Hey Mr. Lum, I'm going to be basically taking you through a tutorial on how and most importantly where all that silly stuff comes from when you're looking at the definition of the definite integral. And I'll go ahead and just write the definition right here. So the integral from a to b of f of x d of x is equal to limit of n goes to infinity with the summation of I equals 1 of f of x of I star, it's a little star right there, x of I star, delta x. So now this is something you didn't teach us this, Mr. Lum, but it's something I found online that turned out to be pretty helpful, because basically what this represents is exactly what you taught us, which is just a plus delta x. So instead of writing two basically equations and plugging and chugging two different things and rewriting this over and over again, because we'll see that we'll have to do that, I'm just going to write x of I star so that we don't have to keep transferring over and over, plug and chug a bunch of other times. So just know that that's what x of I star equal. So now let's see where each of these funny symbols, let's see what each of these funny symbols represent. So starting with the integral from a to b, the integral from a to b basically is on this graph, and we'll say that this is a and this is b, and this is our function. And basically the integral from a to b, bam to bam, is basically it's basically the process of finding the functions above the x-axis, right? And please imagine it as an area. That's what I like to do. I like to imagine it as an area, and that's basically what you typically do when you're doing a Riemann sums problem. So now we're solving for the area of this, and we're going to solve for the area of this by taking the integral between a and b. So since the function, this thing right here, since the function is above the x-axis, I want you to think of it as trying to find the area. And in order to understand what I'm saying, let's see what this equation came from. This one right here. So, let me start from scratch. So here's your typical graph, right? Same one I drew before. Here's your typical graph. Here's your function. Here's your stinking A, and here's your stinking B. Now, let's find the area. Let's find the area by approximating. That's how you have to do it when you have a curved line. Because typically, what do you do when you want to find the slope of a line? Well, typically, our lines aren't curvy. They're just straight up. And in order to find the slope of a line that's straight up, this is a graph. You do y2 minus y1, x2 minus x1, and then you get your answer. But hey, guess what? This is not the same as that, obviously, so we can't do that here. But what we can do is find the area of this, find the slope by approximating. And in order to approximate, you're going to need to start by splitting up the interval into pieces of equal width. So then we'll start by just splitting it up. So bam, 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 bam. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, you always want to have an even number so that even things come out of it. So each piece is going to have a width, and we'll call this width delta x, of course. Blah. Delta x. And basically delta x is going to have a certain value, and its value is going to be represented by the length of this interval right here, of this from here to here. And so in order to find delta x though, let's go over here. In order to find delta x, we need to formulate an equation. And that equation is, this is just a general equation, so there's like nothing you're supposed to know from this. It's not like you're supposed to pull it out of your head or elsewhere. That's going to be your equation, b minus a over n. And what, now that we found our x, we know that each of these increments are delta x. So now let's label the other equations, and in order to do so, we need to find our approximating area equation. And in order to find our approximating area equation, we'll call the endpoints x of I. And that's exactly what we talked about earlier up there. So x of I star equals, like I mentioned earlier, a plus delta x. So now that you know that your x of I star equals a plus delta x, you know what your delta x is, and you know what your a is, now you just got to think of it as a plug and chug type of problem. And we can after now that we know what our x of I star is, before we go any further, we need to find the approximating area equation. And in order to do that, we need to realize that this point right here, right there, we'll call that x of I, and the point right after it, right here, that's x of I minus 1. So basically, you can just think of it as anything after your first point is minus 1. Now let's do what Professor Raymond did best, and let's draw a bunch of rectangles from this point up. And basically, that point in the interval will extend up like we've done so, and until it hits our function like we've already done. So then, after we draw a point up, we're going to extend it to the left and the right, and until it extends basically over the interval. And I already extended over the interval, I just wanted to exaggerate to show you what I was doing. So until it extends over this interval and this interval. So it's going to meet up here, and it's going to meet up to there. Now that we have our rectangle, this thing, now that we have our rectangle, we're going to find our area, right? And we're going to find the area of our ith triangle. Our rectangle, rather. So this rectangle we're going to call ith. Ith rectangle. And we know whenever we're solving our rectangular area, whenever we're finding the area, we always know it's length times width, right? That's elementary stuff. You noticed we've been doing a lot of elementary school stuff, but it's just adding a bunch of other different things that make it seem difficult, but in reality it's just taking it step by step and understanding that it's somewhat elementary. So, like I said, L times W, length times width, is the area of your shaded rectangle. That is fantastic. So what's the length and what's the width of this rectangle? Well, the length of this rectangle is from here to here. And since we know what our delta x is and our delta x is, we basically, well, before we get any farther, I'll just stop and give you that basic idea. So length times width. Now we need to figure out what our length equals and what our W equals. And to find that, we need to write down length times width, of course. Length times width. And then we need to write another way of saying this, and basically write it in the right way, which is the value of delta x equaling the I. and your length is whatever you find after you're plugging in x of I. And so your f of x of I altogether, your length, all that all together is multiplied by delta x. So when we solve for our rectangle, when we solve for our rectangle now, let me erase everything. When we solve for our I-th rectangle, we solve for its area. Area equals, we know that our new equation is f of x of I star times delta x. And we then go over every interval, not just this one, and bold in the bottom of the rectangle, basically, and choose your points. So I'm going to redraw it, and now that we have it's going to be the same exact one, so we're going to have 10 altogether, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, that's the b. So like we said before, this is our delta x. And now basically we're going to find all the rectangles, not just this one. Find all of them. So there's the original one we found. Then there's this one. There's this one. There's it. As you can see, you draw a middle, extend it up, and then once you extend it your left and right, you bring this one up to the top, and that one down, and there you have it. You have 3 rectangles. In the end, what you're going to do is you're going to have a bunch of rectangles in this box, a bunch of shaded rectangles, and basically you're going to add all those rectangles up. But before we do that, let's take a step back and let's calculate the area of the exact same equation we covered earlier. And again, we do this for every interval. In the end, we put rectangles over this entire interval, like I was saying. And after adding all 3 rectangles, 1, 2, 3, after adding these 3 rectangles, we could basically now approximate the area beneath the curve. And the area is going to be roughly equal to the area of the rectangle, and basically plus the area of rectangle 2, plus the area of rectangle 3. So in the end, the shaded part of the rectangle, this part and this part and this part, is going to basically come out, if you want to write it in one equation, it's the area of this, this, and this. Basically it comes out to the area basically being R1 plus R2 plus R3 plus dot, and so on. And on to the theory, because it's just going to keep going on until you have your points. And as you can see here, you're basically going to have 5 rectangles because there's 10 points altogether. So to make it easier to understand, that's what I always like to do. The easy way. There's no other way. Easy button. To make it easier, basically we're going to plug in the formula for the area of the ith rectangle. So right here, we're going to plug that baby into this equation. And it's going to come out to be f of x of I star times delta x plus x f of x of 1 star times delta x plus f of x of 2 star delta x plus, you get it. You get the point, guys. What I'm trying to say is that what I'm trying to do is just simplify it and make it easier. Dot 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 r n, or in this case an rn f of x n star delta x. So this is a long equation, as you can see, and in order to somewhat simplify it, we're going to write the summation symbol, because that's what summation does. It sums it all up. So we are going to say that n of the summation of I equals 1 times f of x of I star times delta x. So that equals this, just reduced significantly. And the Raymond's theory basically demonstrates that the more rectangles we use when we're approximating, the more accurate our answers will be. So in order to mathematically represent that, you want to say use a bunch of rectangles. We're going to need to basically let the limit, like we wrote before, let the limit of n goes to infinity be the summation from I equals 1 to n of f of x of I star times delta x. And since this is approximation, it's just what we use in rectangles. We're not letting the number of rectangles go off to infinity. And as the rectangles increase in number, the better and closer our approximation of the area gets. But by calculating that limit right here, we can say that the true area underneath the curve would therefore be the limit of those approximations, essentially. So that's basically where everything comes from. And there are a couple other things that I'll cover in another video, but this is essentially where the definition of the definite integral comes from. And I'll go ahead and write that out and basically bring it all back to an end. It's basically where this baby comes from. The integral from a to b of f of x times d of x equals the limit of n to infinity of the summation from n of I equals 1 f of a x of I star delta times delta x. So thank you, Mr. Lum, for reviewing this video. This is basically what I think of whenever I do any Riemann sums problem, and I'm hoping that it will help any other student. Thank you, Mr. Lum.